This is part 4 of the lecture Linear Systems and their Diagonalization. Here we'll be looking at the importance of the Fourier transform because sinusoids are eigenfunctions or eigenvectors for convolution operators, for linear shift invariant operators. So we'll also look at the discrete Fourier transform in matrix vector form and consider delta and Fourier basis vectors or basis functions. So as we know, a simple model for 2D back-projected PET data is convolution. And so what I'm showing on this slide are example input, true objects, if you like, one point source, multiple point sources, and in the back-projected output we just get the point spread function located at each location of those input point sources. More general distributions, again, can be regarded as point sources of different intensities, and so therefore the back projected images are just point spread functions with corresponding scaling of the amplitude of those point spread functions. We've also got noise going on here as well, which we will consider later. So this is another look at example input images to the forward projection process, the acquisition process of a PET scanner, followed by back projection of the data. And so the inputs are on the left-hand side here. The acquisition and the back projection is denoted by these arrows. That's the overall system that we're considering here. And so again, we have point sources being replaced by point spread functions. In this case as well, where this is a Shep-Logan phantom, again a collection of point sources of different intensities. So likewise the back projected image, a collection of point spread functions of corresponding intensities, linear mapping and shift invariant. However, take a look at this very interesting case here. This is a two-dimensional sinusoidal function. It's a little bit artificial, but it's nonetheless very important to understand. It's artificial because obviously a sinusoidal function has negatives in it and we can't have negative radioactivity. But if you can accept that for the moment, if we run that through an acquisition and a back projection process, then look at the output here. Do you notice anything special? I hope you do. I hope you notice that this function is identical to the input function except for some scaling factor. And what we find is that the higher the frequency of the sinusoidal function here, typically the lower the intensity of the output when it's run through a forward and back projection. And so that would correspond to effectively a low-pass filter, where, or effectively something like a low-pass filter, where low frequencies are transferred through that overall system relatively efficiently, whereas the higher frequencies are very much attenuated by that forward and back projection process, which of course makes perfect sense because one of these point sources just gets replaced by a rather blurred PSF, and so it's what we'd expect. In other words, we're losing the emphasis of the high frequency components. Going to a very simpler a much simpler system, just a 1D case now, and this happens to be an example or some piece of electronics, if you like, that is taking input signals of various types, and then it is outputting some output function. And the reason for showing this is that, here's the impulse, that's equivalent to a point source in an imaging context. We're getting some kind of impulse response function analogous to the point spread function. We've got all these different signals, but look at what happens when we put in a sinusoidal function into a linear, in this case I guess linear time invariant, but directly analogous to a linear shift invariant system. What we get at the output here is an identical sinusoid, in other words the same frequency sinusoid, it's the same function, whereas look at all these other cases, the input functions do not look like the output functions at all. But here, the input function is identical in functional form to the output with just a scaling, okay? So sinusoids pass through linear time invariant or linear shift invariant systems with only a scale factor of difference at the output. So that is quite a remarkable result, and it heavily motivates the use of Fourier analysis, as we will see. So sinusoids then are what's known as eigenfunctions of the convolution operator. And that's because they're treated in a very simple, very special way, by LSI systems. So here, imagine therefore that was the input sinusoid, so it's just a cosine function, a spatial cosine function going into, imagine a 1D imaging system for the sake of a simple example. Frequency, spatial frequency k, so it's just a cosine function. And if it's run through a system denoted here by this operator S and curly brackets here, it's going to give us some output function from an output of the mapping, an output of the operator. Now, if that operator, if that system is a linear shift invariant system, then this is the remarkable outcome that we have, which is that that output function is identical to the input function, because the input function here was cos kx, the output function is cos kx. All that has happened to it is that it has been scaled by some value h, okay, which depends on the frequency of the sinusoidal function. So for frequency k, therefore the scaling factor, it depends on that frequency, that spatial frequency k. And so this scaling factor of this eigenfunction or eigenvector, that scaling factor is known as the eigenvalue. Okay, and so this is really beginning to build up to where we're going with the whole of these, the parts of this lecture. This is heading towards the diagonalization of a linear mapping, okay? And we can do that through use of the Fourier transform for the case of a convolution operator. And later on, we'll see that we've got more general ways of diagonalizing more general linear mappings that are not shift invariant. So I'm emphasizing in the bottom right corner there that for the discrete case, we talk about eigenvectors, but colloquially, we'll often talk about eigenfunctions, eigenvectors almost interchangeably, just as we would talk about functions and vectors interchangeably. Obviously, you should be more rigorous when you are doing scientific writing, but just to be aware of the notation and nomenclature that is used often casually in presentations as well. So given that special treatment of sinusoidal functions by linear shift invariant systems, this is a fantastic motivator for Fourier analysis. Why is that? Well, Fourier analysis, or here, Fourier synthesis, is saying that more or less any function f of x, this is just the 1D case, so a spatial function, so again in the PET context, that would be like a radioactive concentration f as a function of position x along some line through the brain, for example. We're saying that that function is equal to a summation of sinusoidal functions. So this is a complex exponential, that's just cos kx plus I sine kx. And so it's a sinusoidal function, and each sinusoidal function just has a unique weighting factor, f, which depends on the frequency of that sinusoid. And then all we do is we sum together all of those sinusoids, and from that we can synthesize, or if you like, reconstruct our function f of x. Therefore, our function f of x can be expressed as a summation of sinusoidal basis functions, which is great news because we know that those sinusoidal basis functions get treated in a very trivial way by linear shift invariant mappings. So let's look at that in discrete form. That was the continuous form. And notice actually this was the inverse Fourier transform, okay, because that's the Fourier synthesis, if you like, where we're synthesizing a function by summing together complex exponentials. In the discrete form here, I'm now assuming a limited number of samples, so strictly actually this is going to be a periodically repeating function. And all we're saying is a discrete vector f, obviously it's discrete, a discrete function f here, is just given by complex exponentials. Okay, this is just like a fundamental unit of frequency and just integer index to indicate the overall frequency. So the k here has just been replaced by this expression here. And that complex exponential is just weighted by some amount, capital Fn. That's the amount of frequency n, okay, that is present in the signal f or the image f. And all we do is just sum together all of those complex exponentials, each with a unique weight, and then we can reconstruct, we can synthesize our original vector of interest. In matrix vector notation, I'll illustrate this in a moment, we can just say that that's the input vector f there, so that's just here. And then this, notice that we have a frequency index n and a spatial index x. And so that's, if you like, two independent variables from which we can create a matrix. And so here f is just a set of weighting factors for each of the frequencies n that is considered to be present in f, the function f. And so s and the index x here is just giving us the spatial position along a particular sinusoidal complex exponential function. And then we just sum together over all of the frequencies, so n equals 0 to n minus 1, to recreate, to synthesize our function, our vector f. And so there it is in very compact notation. So I'm using this rather awkward capital F here for the Fourier coefficients, but I think you get the idea, and feel free to use your own notation. And I'm using a capital S to denote a matrix that contains the Fourier basis vectors. In other words, those complex exponentials of every frequency just stacked, as just columns inside that matrix S. And from that we can create our vector f. So here is a very crude illustration, just to give you the idea. Please don't take this as something exact. I'll do the exact version presently. So what we're saying is a signal or image, an output vector, is given by a Fourier coefficient of a first basis vector, a Fourier coefficient of a second and third and fourth and so on. So we have all the Fourier coefficients here in this input vector, and each of them is a weighting factor for each of the sinusoidal basis functions that are stored in columns of that matrix, capital S. Okay, so that again was just an illustration, just to show that we're using Fourier coefficients as weighting factors for complex exponentials to add them together to create a signal or image, to synthesize it. Now being more precise, in fact very precise now about the contents of that matrix S, if you were to go into MATLAB and type in DFT MTX brackets 4, that would give you a 4x4 discrete Fourier transform matrix, just to really spell it out explicitly. So this is for the inverse Fourier transform, which means we've got the complex exponentials for each of the frequencies under considerations. This would be frequency 0, frequency 1, and then this is the maximum frequency, known as the Nyquist frequency, and then this would be like the negative frequency. In fact, it depends on how you decide to order the data, but you can see, I hope, in fact it'll become clear at the bottom right corner, that that's a constant valued function, which is like cos of 0. This starts at 1, goes down to 0, goes down to -1 and back to 0. That's like the first frequency, just fitting in one waveform over those 4 samples. And here, for that third column, we're now fitting in, if you like, 2 waveforms. In fact, that's the Nyquist, it's the maximum we could fit in terms of frequency into just 4 samples. We can just fit in 2 whole waveforms there. So 1 - 1, 1 - 1. And so that's the cosines, and these are the sines contained, because you know e to the I x, or e to the I kx is cos kx plus I sine kx, and that's exactly what we're seeing in that top left corner there. So this is sine of the 0 frequency, it's just 0, at the first frequency, and then at the Nyquist it's also 0 as well. It's just where the sampling lies for that sine function. It just kills it off completely, it just hits the zeros. And that's the positive first frequency and the negative first frequency. And then so that's the inverse Fourier transform. So was that matrix S that we've just been looking at. And if we wanted to do a Fourier transform, we'd have to use the conjugate transpose of that, where we just interchange rows and columns. I'll go through the mechanics of that in a moment, so don't worry about too much about the top right corner, because we've been focusing for the moment on the Fourier synthesis, adding together complex exponentials. So if you were to now go to DFT MTX 256, I think it is, yes, here, then the real part, that's that bit there, the real part, those cosine basis functions would look something like that. This is just for 1D functions. Of course, it would look even more involved if you got into 2D sinusoidal basis functions. And in reality, we don't use DFT matrices, we just get on with the job and use a fast Fourier transform in 2D, for example, or in 1D. But this is showing what's actually going on, because it's really important to understand that. And then if we were to visualize rows of this matrix here, you can see that there's the zero frequency, that blue constant line, that's cos of 0. And then we get the first frequency, which is that green one, the second frequency where we get 2 waveforms, that's the red one, and the third frequency, which is 3 waveforms fitting into the 256 samples, which is that cyan curve there. And so something similar can also be shown for the imaginary component, just looking at the sine functions of the imaginary part of the DFT matrix. Okay, so we've covered the Fourier synthesis, the inverse Fourier transform in the continuous form, and now also in the discrete form, and matrix vector notation for that. So how do we get those Fourier coefficients? Well, it's a very simple process. You take the function f of x that you wish to express in the Fourier domain, and all you do is take that function and you multiply it by the complex exponential for which you wish to find the coefficient, except with a negative in the argument there. So I do lectures elsewhere on explaining why that is, but in a nutshell, if we're trying to find the coefficient for e to the ikx present in f of x, then we need to multiply it by e to the minus ikx, because the ikx cancels with the minus ikx to give e to the 0, which gives a finite result because it's a value of 1. And so it's a finite result on integration. And so it will give us, it will pick out the amount, the coefficient for e to the ikx that is assumed to be present in f of x. And because of the orthogonality of these sinusoidal basis functions, whenever that e to the minus ikx is multiplied by any other spatial frequency present there, you'll get a function that's as much positive and negative, and when you integrate it, it gives a net result of 0. That's the benefit of orthogonality of these basis vectors, and so that's why we can find the coefficients for the complex exponentials just by doing this very simple product of the two functions, point-by-point multiplication, and then summing, okay? So effectively, it's just matrix vector again, so it's just a scalar product. So if you like, this is just a discretization of that continuous description here. So again, I've already talked you through the k there is just given by this with an integer index n for the frequencies now. And you can see it's just f of x gets replaced by that vector. So it's just point-by-point multiplication of a complex exponential with your input vector. Sum it all up, normalization, and that gives you the amount, fn, of complex exponential e to the minus in 2 pi over x that's present in f of x. So it gets much simpler in matrix vector notation. So that negative in there, that corresponds to the complex conjugate. And so what this amounts to, again, don't have time to explain it all here. This is for material for elsewhere. But it's basically the conjugate transpose of the matrix S that we've just looked at that will give us the amount of frequency n that is present in the function f of x. So far more elegant in matrix vector notation, barring my rather clumsy capital F here for the Fourier coefficients, but again, it's up to you if you want to change notation. So there we have now S star, that's the conjugate transpose of the matrix S. In other words, we just take the complex conjugate and then interchange rows and columns. That's how we get from S to S star, and that gets multiplied by the input vector F that we want to express in the Fourier domain or in the k-space domain, and that's what that expression is doing. Okay, so here it is again with a very simple illustration. Please refer to the previous diagrams where I gave accurate descriptions of the discrete Fourier transform matrix. This is just to display an illustration and the concept of the scalar products that are at work here. So we just take the first frequency, multiply it point by our input signal or image, and then do the summation, and that gives us the amount of that frequency that is present. So this basis function gets multiplied point by the input vector, and then you sum up the result. Obviously there are scaling factors involved in this, and that gives you the amount of that frequency present. So that's just a visualization of the concept of S star multiplied by F. Okay, so I just want to finish with a further brief note on Fourier analysis. So consider this very simple case of a 2-pixel image. We'll see why it's 2 pixels, because it allows us to visualize what's going on very easily. Or indeed, we could consider this as a 2-sample function. Anyway, let's consider it as a 2D image with just 2 pixels. We're going to say that that vector f is just equal to a coefficient times this basis vector. This is like a delta basis vector or a canonical basis vector. It's just 1 and then 0. Plus f2 times this other basis vector, other delta basis vector, 0, 1, where the delta function's just been shifted on to the next pixel location. So this is all quite a trivial example, but we'll bear with it for the moment because of the benefit that we get for understanding the Fourier basis vectors. So we can express this vector f as some coefficients in general, coefficient vector c, for basis vectors stored in a matrix, which here I'm going to call a matrix D. So here we are, then this is the synthesis expression. Output vector f is equal to some coefficient vector c operating on a basis vector matrix D. So I'm now writing that out more explicitly. I'm saying that this matrix D is composed of a vector D1, and so that's this vector here, 1, 0, and a vector D2 for the second column. So that's this vector here, 0, 1. And I'm now, and again, I've still got the coefficients just sitting to the right there as a vector. And so writing that out more fully, it's just 1, 0, 0, 1, and then the coefficients vector is C1, C2. Now, of course, we can see this is very trivial for this case, but we've just got to bear with it because of the insight that we'll get in a moment for the Fourier basis vectors. Okay, so that's the expression where we're saying f is equal to some coefficients multiplied by a basis vector matrix. So how would we find the coefficients vector c? Well, you know, assuming that D has an inverse, and it certainly does in this case here, we would just go about inverting that matrix. So c is equal to the inverse of D times f, all very straightforward. Because the matrix D is orthogonal, because these are orthogonal vectors, but of course more than that, it's the identity matrix, so it's bound to work. But anyway, let's follow it through. These are orthogonal basis vectors, and so therefore the inverse is equal to the transpose for an orthogonal matrix. That's one of the benefits of an orthogonal matrix. And so therefore C can be found just by doing the transpose of D and operating on the vector f with that. So just following that through, D transpose is going to be that column now, D1, that basis vector, placed along the row now of this matrix. And then we've got the second basis vector, which was column 2 of the matrix D, now placed along the second row of D transpose. Of course, hard to tell the difference here, but anyway, there it is. So it's 1, 0 and 0, 1 applied to the vector f. And so sure enough, what drops out the other side is just simply f. In other words, the coefficient vector c is none other than the vector f, as expected for such a trivial choice of basis vectors. Right, so hopefully now that'll set us in good stead for understanding the Fourier basis vectors a little bit more. So now then we've got that same 2-pixel image with values f1 and f2, just a 2-element vector. And we're now saying it's equal to some Fourier coefficient f1 for the 0 frequency component. And what's the 0 frequency sinusoidal function look like? Well, it's just a flat function. It's just cos 0, which is 0 frequency, and the cosine of that is just equal to 1 everywhere. Sine of 0 is just 0. And then added on to that would be the other Fourier basis vector, which for just a 2-pixel case, we can only fit in 2 frequencies, the 0 frequency and what's called the Nyquist frequency, the maximum frequency that we can fit in there, which is just up and down, just one waveform. And so that is the next, that's the frequency 1, if you like, which happens also to be the Nyquist and maximum frequency. Anyway, so here we are. This is just, if you like, conventional Fourier synthesis saying a vector f is just equal to coefficient of the 0 frequency plus a coefficient of the first frequency. Okay, so that's the Fourier synthesis expression there, or if you like, the discrete inverse Fourier transform, where we've got this sort of a small capital F there as the Fourier coefficients, which act as weighting factors on this matrix of sinusoidal basis vectors. So that's basis vector S1 and basis vector S2. There's S1 and there's S2. And by adding those two together with various weights according to the Fourier coefficients, we can then reconstruct, we can synthesize our original vector f. So this is just expressing our vector f as a superposition of sinusoidal functions. So spelling that out then, so there's the 1, 1 for the 0 frequency and 1, minus 1 for the Nyquist frequency. And we've got f1 times the first column plus f2 times the second column. Add them together, we get f. Fine. Okay, what are the coefficients? So let's take a look. Because S is actually a complex valued matrix, remember we've got the cosines and the sines in there as a real matrix and an imaginary matrix. The generalization of an orthogonal matrix, remember the orthogonal matrix was one where the inverse is just given by the transpose. Well, for a complex matrix, we talk about if the matrix S is unitary, then its inverse is given by the conjugate transpose. Okay, so where were we? We were saying that there's the Fourier synthesis, and we're saying that our vector is just expressed by a summation of sinusoidal basis vectors, and we want to know what are the coefficients for them. So what we're going to do is just invert that, assuming the inverse exists, and it does. This is a unitary matrix. So the Fourier coefficients vector f is just equal to s minus 1 operating on the vector that we want to decompose, so f. And because S is unitary, we just take the conjugate transpose of S, and so that means you just take the complex conjugate of each of the complex values and then interchange rows and columns. So that's S star F, which we've already seen before earlier on, is none other than doing the Fourier transform, okay, where you just take each basis vector as a scalar product with the input vector F. We've seen that illustrated already, and so that is giving us exactly what we expect, and that will deliver f1, the Fourier coefficient for the first Fourier basis vector, so the 0 frequency, and then f2, the Fourier coefficient for the second Fourier basis vector, which is of frequency 1 and also equal to the Nyquist frequency. So I've left out the normalizations here, but I hope nonetheless it's clear what I've been doing here. Okay, so all of that has taken us to this slide, which is hopefully of use for conceptualizing and better understanding basis vectors. So there's our 2-pixel image, f1, f2. Could also be visualized in this way, almost like a 1D discrete function with just 2 samples, f1 and f2 at location j equals 1 and j equals 2. Okay, 2 pixels. So using the canonical basis or the delta basis vectors d1, d2 that we've already seen in the previous slides, there's the basis vector d1, there's the basis vector d2, and then we're saying that f is equal to some amount f1 of d1 and some amount f2 of basis vector d2. Okay, that's what we saw earlier. But now the interesting example is to see what happens with the Fourier basis vectors. So remember they're S1 and S2, so 1, 1 and 1, minus 1. So let's take a look at the zero frequency. That's the cos of zero basis vector. So that's where we've got 1 and 1. Okay, so that's what I've plotted here, and that vector S1 is equal to a pixel value of 1 and a pixel value of 1. Put them together and we end up at that point in our two-dimensional space. Okay, and then we can see that our, well, maybe let's just do the other basis vector first. S2 is the other Fourier basis vector, and so that's 1 and minus 1. So we go distance 1 along the basis vector d1, and then minus 1 in the basis vector d2, because it's 1 minus 1. So 1 minus 1 takes us down here. Okay, so that's the second Fourier basis vector, S2. Now, our original vector f, we can now see how easy it is to express exactly that same vector in two different bases. So with the delta basis vectors, or the canonical basis, the vector f, we can just project it onto d1 to find the coefficient of d1, or project it onto d2, which is the coefficient of d2. And if we want it in the Fourier basis, then all we do is project it onto basis S1 and we get the amount F1 for that basis vector, or we project it onto the second basis vector and we get the amount F2. And that's doing those scalar products of the conjugate transpose of the Fourier basis vector matrix, the scalar products of each row with the input vector F. It's just projecting it onto an orthogonal pair of basis vectors. So you may have heard about that expression before, and I hope this just now clarifies that for you. And you can see here I've just spelled out the two Fourier basis vectors in the same space as the original function f, just for further clarification. Okay, thanks for listening to this lecture. The next part in the series is part 5. And it's a demo of the Fourier transform. In case you feel you need a bit more insight into what's going on in the Fourier transform, then I suggest you watch part 5. Otherwise, feel free to move on to part 6. Thanks for listening.